in this part, we will look into working set. Basically, this is a technique used to handle trashing in most of the operating systems. So here, the key observation is to capture the locality of a process. So, so the way we can prevent trashing is by keeping the set of pages that are needed by a process so that we can avoid a lot of the page faults that are made by the process. So the graph on the slide shows the number of page faults as the number of pages in the memory is increasing. So as we increase the number of pages that are needed by a process in the memory, the page faults rates naturally decrease because pages that are needed by the process are all in the memory, right? So initially, when there are very few pages, the page faults rates will be high. And as we keep on increasing the number of pages for the process, the page faults rate decreases. And we want to capture the optimal number of pages that are needed by a process that will decrease the page faults. Okay. So this number of pages is what we call like working set. So how can we formalize this? So working set model, this is proposed by Peter Denning. He was Purdue CS head during 70s. So here, the informal definition of working set is a collection of pages that a process is working within a given time interval. And these pages should be present in the memory to avoid thrashing, because these are all the pages that are needed by a process during that during the current time interval. Okay. And how can we implement this? Like, how can we turn this concept into an implementation? To do that, first we need a way to capture the working set. Okay? And then once we know the working set, we need to modify our page replacement algorithms so that they take care of this working set and not replace the pages that are part of certain working set. Okay? So how can we capture working set? So as I mentioned before, working set size, or like the working set, is the number of pages that are needed by a process for a given time interval. Okay. So first we select working set parameter called delta, that is the time interval. So at any given time t, the number of pages, the number of unique pages that are accessed by the process for the time period delta is the working set size. So here, as we can see on the slide, if there are given, those are the page references. So here at time t1, working set size would be 1, 2, 5, 6, 7. However, at time t2, the working set size is pages 3 and 4, because those are the only two pages that are referenced within that time interval. And note that the working set size actually changes with the program, because as the program is executing, its locality changes and the accesses that it makes changes, therefore the working set changes as well. And over few periods, you may have a larger working set and some periods may have smaller working set. It depends on it. It depends on how the program is accessing its data. And our goal is, given a working set, we always should make sure the working set or the pages that belong to the working set are always in the memory. So here we need to, in case of working set model, first we need to choose delta, the working set parameter. And at any given time, we should have all the pages that are referenced by the process in the last delta seconds, which is our working set parameter and which constitutes the working set. And we should not execute the process if the working set that is declared, like that we identified using delta, if those working set pages, if they are not in the memory, we should not execute the process. Because what happens if we execute the process? Thrashing. If we try to execute the process without pages in the working set, the process will keep faulting because it needs those pages. That's why thrashing happens. Okay. So once we identify the working set, now let's see how we can modify our page replacement algorithms to take working set into consideration. So here, let's see how we can modify FIFO. So here, FIFO with second chance, everything is same except when we have the reference bit 1. So we clear the bit. When we clear the bit, we also record the timestamp for that page. Okay. And if the reference bit is 0, we check the last use time of that page. Okay. And if the page has not been used in the last delta seconds, that means it's not part of working set. So we just replace the page. Otherwise, we go to the next page, so on and so forth. Okay. So the only note that the only minor modification is when we have the reference bit 0, we check the last use time and we ensure that the last use time is not within the past delta seconds or like within delta. So similarly, we can modify our clock algorithm, which takes care of both reference bit and modified bit as shown on the slide. So here everything is the same. However, when the reference bit is 0, we check the last use time, and if the last use time is within delta, we go to the next page. However, when the last use time is not within delta and the modified bit is 1, then we just mark the page for page out and we reset the modified bit and we go to the next page. If the page is not used within delta and the modified bit is 0, that's very good because that's our victim page. So we always replace that page. Whereas if the modified bit is 1, we just reset the modified bit and we mark the page for page out and we give it second chance, right? We go to the next page. So although the working set algorithm looks simple, there are certain challenges in implementing working set algorithm correctly. Specifically, how to choose the working set parameter, the delta, how to choose the number of seconds that we should give for each process. And this delta could be different for different processes. Okay. And what happens if we pick delta that is too large? Okay. In that case, we may be underutilizing the memory, right? We may be keeping more pages than that are necessary to avoid trashing. What happens if delta is too small? Then of course trashing happens. What happens if delta is just like 1 nanosecond? So in that case, we will not be able to capture the locality of a process correctly. So the pages that are needed are not present in the memory, so thrashing happens. So it's really important to choose delta correctly. And this also and working set also gives us a very nice way to control the number of processes that we can run smoothly, right? So if we need to make sure that we run those many processes whose working sets we can put in the main memory. If their working set exceeds the available main memory, then we should not be executing those many processes. We should either kill the current processes or we should stop or like block few processes until the main memory, until there is space in main memory to accommodate their working set. So, and working sets in real world on real processes, they vary with time. So here, the working set size is on the y-axis and the x-axis is the time. So as the process keeps on executing, the working set size increases. And once the process reaches stable state, the working set size uh, stays constant. So here there are many plateaus and there are few stable lines, right? So the plateaus indicates the transition state. That means either the process is like made a function call and it is executing a new function, and the stable state indicates when the process is actually doing a certain loop or it is just executing the same code again and again. So so in simple words, you can imagine like the bumps to be like new function calls where the locality is changing, right? And the stable points are indicates the locality. Stable points indicates the process is actually having a good locality. Okay, and the peaks indicate the transitions of locality. Okay, and There are even more challenges in capturing working set. Like working sets are not static, as we saw before, they change with time. And furthermore, the size of the working set could also be different at different times. If you see our previous uh, slide, so here the working set in this third stable state is actually more than the working set size in the second stable state. So even when the even when we have good locality, the working set size changes with the process along time. Okay, and it also varies with the coding style. For instance, let's consider simple matrix multiplication, right? Depending on whether you do row order processing or column order processing, the locality changes, right? And it also depends on how you store the array in the memory. So if compiler decides to store a multidimensional array in row order, then the locality would be different from storing the memory in column order. Okay, and working set size is it's hard to measure for non-traditional programs such as interactive programs, because like how to measure the interactive programs working set, because it varies with the user input. It varies a lot with the user, right? So like user like the graphical user interface, of course it's part of working set. However, depending on the functionality user clicks, the working set could be way different for different use cases. And furthermore, like what happens to working set if the pages are shared between multiple processes? So in that case, we as we saw in the previous in the page replacement algorithms, we kind of look for at each process. However, when a page is shared, it could be used by different processes for which we may not be able to observe their accesses. Okay. In that case, it's hard to measure working set when pages are like shared by different processes that are actually executing on different processor. Okay, that's the end of the part. And in the next class, we will review all the concepts that we have learned in virtual memory and see how they tie together to the whole operating system uh, concepts. Okay, thank you.